Good afternoon, everyone. Welcome you all to this year's first network seminar series hosted by the Center for Network Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Dr. Sushovan Das. He will be speaking on re-architecting data center networks, a new paradigm with optical core and optical edge. Dr. Sushovan Das is a postdoctoral researcher at ETH Zurich in the Networked Systems Group led by Professor Laurent Wenweber. He received his PhD in computer science from Rice University in 2024, advised by Professor T.S. Eugening. Prior to that, he completed M.Tech from IIT Kharagpur under Professor Debashish Datta and B.Tech from Jadavpur University. His research primarily focuses on designing novel and energy efficient optical network architectures to optimize diverse application performance in next generation cloud infrastructures, bridging theory, and system realization. The audience is encouraged to ask questions at any point during the talk. For those who are attending online, questions may be asked either by unmuting and speaking directly or by typing them in the chat box. Over to you, Dr. Das.
Thank you. Thanks a lot. May I start? Okay. Thank you. Thank you all for being here. So it was a very late thought, and I contacted all of you guys, and thanks so much to arrange these things within a short time. So yeah, so I will be talking about a new paradigm of the data center architectures with optical core and optical edge. So I will introduce each of these terms with you slowly. So let's first start with the overview of data centers, right? So I guess the name suggests what it does. So basically, this is the infrastructure like behind cloud. So cloud is a buzzword. We know we run lots and lots of applications like large-scale AIs and so on in cloud. So what actually cloud is? Behind the cloud, there are large-scale data like warehouses with millions of servers, which are basically compute and like storage nodes. And it looks like this. So this is one of the examples of Google's data center in like the States. There are many more. So basically, you can see these boxes. So these boxes are called rack, and the servers are generally organized in racks. And now basically these racks are getting connected via a network of like switches, which we call like the data center network. So that's our context here. So now let's try to understand what is inside this architecture, what we need to understand. So the data center network looks like this. If you see this bottom thing, which are basically the circles are the servers, again, it can be CPU, GPU, TPU, whatever you can think of. And they are connected via a multi-layers of commodity Ethernet switches. All these boxes are the same thing. So it can give you like the economy of scale, so it can scale well, you can buy in mass, right? However, based on which locations, logical locations these like switches are, based on that, the names change basically. So as I kind of started, right, you saw the servers were inside those boxes, which we call rack. Every rack has a switch on top, which basically called TOR or top of rack switch. And then basically, if two servers of like two like separate racks need to communicate, they need to go through another layers of switches, which is called aggregates. And even further, like servers, they need to go through this core switches. So generally, this is the very, very typical architecture that you can actually see, which we call like folded claw or fat tree kind of architecture, because the core is very fat. It looks like a tree, right? So overall, right, I will introduce two terms here that for the sake of understanding, we call the network area beyond the top of rack switch as the packet switch network core, and the lower part we call as the edge, which is basically consisting of server and TOR for now. Because I will use these two terms after some time, and you can actually see what we can do. Okay, so that's the basic background. Now, as I said, the data centers are hosting a diverse variety of applications at these days, starting from high performance computing, like scientific stuff like weather forecasting and fluid modeling and like whatnot. And these days, the booming application scenario is large scale AI ML applications, which uses like millions of like GPUs. DNN trainings and stuff, as well as other cases. So all these applications overall, they have like stringent performance needs. They both need high throughput and low like delay. And if you see like generally, if I just split this applications based on what kind of phases they actually go through, it has two phases. Some part of it actually is the kind of the compute phase, where the node, the actual GPU or the server is computing something, and then they need to exchange the data across those like GPUs. So overall application runtime is basically sum of these two phases, compute and the network phase. Now, compute phase is getting faster and faster because you are getting accelerators like GPU, TPUs, and all. They are absolutely making it like tailor-made hardwares. So now the pressure is shifting towards the network side because the network timing component is getting bigger in terms of the overall application runtime. So if you actually can save even 20% network time, it can reflect as kind of significant improvement in the application runtime. So that makes it more interesting for us, right? So what we need to do, the simplest thought is that you just need to scale up the network. You need to have faster and faster packet switches. So what is the challenge there, right? So is it easy to do at this time point? So there comes the area of my work actually, right? It's not so easy to scale up the switches anymore because of the challenge coming from the post Moore's law era. What it says is basically the Moore's law of networking. The similar Moore's law exists for the CPU side. What it says that the electrical packet switches cannot really sustain now for the long run because of increasing gap between the switch capacity or the speed versus its power, cost, and the port density. So it basically looks like this. So if you can see in the last 10 years, actually, there has been multiple generations of like ASICs that are coming in the market, right? And you see that the speed is almost like more than like doubling, right? But at the same time, you see the power consumption of the ASIC is also like growing almost like linearly and maybe like faster at these days. So I showed you the data of the fastest switch ASIC we had until the end of 2022. By now, we are already 4 years later, and we actually have 102.4 terabit per second ASIC available. I don't have the full data because they will be launching very soon, the things, but the things are there already. So overall, the point is, if you actually see that, for example, the Broadcom, so these are all like Tomahawk ASICs, and the kind of company is called like Broadcom. They make this kind of like ASICs, which is one of the popular thing for the data center switches. And you see the power, the Tomahawk 5 ASICs has more than 45% consumption of power than the earlier generation, right? So basically the question is like, what next? So you just cannot simply speed up the switches anymore. You have a price to pay now. And what is the price? Let me tell you more. Now, the price is coming from the energy budget of the data centers. So generally, if you can imagine, you have a big scale data centers with say 60K servers, and this kind of 51.2 terabit per second switch, which is basically 64 port switch with 400 gigs per port. Such a network would consume, the maximum power consumption can be around 50 megawatt actually, because you have multiple layers of switches, lots and lots of like wide scale network, right? So maybe the absolute number itself is a small fraction of the overall budget, but the number itself is like scary, right? It's megawatt order. So you can see already this number is way beyond the energy budget that the operator generally keep fixed to run a cloud. Because you can actually think of this part of this power consumption will reflect it into the operational cost of it, because you need to pay the price for every month. It's not a one-time cost. And another point is that obviously this cost, or like this power value, what we are showing here, that is more like kind of like considering the fact that the switch is operating at 100% utilization. It's processing packet all the time. Then that will be the maximum power consumption, which is not an unrealistic assumption anymore, because for AI clusters, the goal is you need to minimize the network timing almost to zero. So the network has to be super fast, and the switches are almost utilized all the time. So that makes this thing even more scary. So overall, right, the summary is, again, this packet switch based core is consuming a lot of power. You just cannot really simply go through a faster switch architecture. So we are stuck, right? What to do? So in the last 5-6 years, people have been thinking of like we need to like rethink this problem, because you just cannot use the same product anymore. One of the idea that came in is, let's replace the most of the packet switches from the core by low power optical switches. I will tell you more about what is special about it. So the term here is important, is optical circuit switch. So the principle of operation is not the same as the packet switches, right? But one thing I will first tell you here, that by that I'm trying to sell this thing to you guys, that the power consumption of this kind of like switches are almost zero or null. In most cases, it's like zero. So generally, the idea is, let's keep the server and TOR, and then replace the higher layer packet switches by an all optical architecture. Okay, so that can save your power. But is it like, then how the network will operate? Would you use the same algorithm, same ideology here? Maybe not, because the kind of the operating principles are not the same. So just some quick background of the basic building block. As I said, this optical circuit switch, right? So basically, it is a physical layer switch which can steer light from one port to another port. It's optical, so it doesn't really understand the packet. It understands the light stream, and it can actually, you can program this kind of like switches to say that, okay, if a light is coming at port A, I want to send it to port D. Simple stuff. You can actually do it. So it has like a DSP internally, which can very cleanly rotate the meters. That is one way of doing it. There are many other types of hardwares are there. By that, you can actually have the input light to port mapping. So which basically gives you a circuit at the very abstraction level. And you can do it at runtime like this. So obviously you need to pay a small price, which is a downtime, because it's not, the circuit setup is not instant. So the fortunate thing is that the downtime is getting smaller and smaller in the last few years of the evolution of optical switches. So there are MEMS. MEMS means like the mirror. You need to rotate those like the mirror like assemblies to connect to specific ports, which is obviously slower. So the order was in tens of milliseconds. But from there, we are actually having this AWGR kind of switches. I don't go into low level here, but these basically AWGRs work on this principles of like, you have a glass, you have some like the patterns, like the gritting stuff, and whenever you actually send the light of a certain color, you can actually control that it will come out with a kind of a constructive interference or not. So by that, you can which is we call like wavelength routing basically. So if you change the color, you know from which output port it will actually come out, and that matrix is fixed. So with that, you can play basically. So that is much faster, because you don't need to rotate mirrors and stuff. So here we are kind of order of like nanoseconds now. So obviously the advantages are there, right? This is agnostic to the speed, because it deals with light. It doesn't need to process packet at a certain speed anymore. And because it doesn't have to process packet, to buffer packet, the forwarding latency is null, almost like zero. And obviously, due to this small amount of functions, it's more simple than packet switch, which has many functions, right? So the power consumption is much smaller, actually, and almost like zero. However, the main thing to note here, apart from this advantage you got, the philosophy has to change now, because you cannot really change your forwarding entry or the port-to-port mapping for every single packet, because it's a bit slower than the typical packet switch. So in a very hypothetical idea-wise, packet switch is a very fast circuit switch. You can actually imagine, which can create circuit for every single packet. Now, a typical circuit switch can create circuit for a collection of packets. So by that, you can actually amortize this price of downtime. But you can actually, but the point is the applications we are dealing these days, they are becoming more and more friendly with this kind of idea like AIML. So you exactly know which set of nodes will communicate for how much amount of time. And the same thing will happen across the iterations for like thousands of times. So these are more like a circuit friendly scenario. You can create circuit early on, right? Okay, so overall, that's the idea that why circuit switch can work under this context. So now just to give you a bit more thing to kind of be happy about is that the optical circuit switching is like in the data center is like real. It's not the textbook thing anymore. Like Google, Microsoft, they are all actually adopting this stuff because they are really having a pain to maintain the massive power problem. So they are replacing their cores with low power optical switches. For sure, they don't really use it in a very smart way because that takes time, but they're at least having a bandwidth transparent layer which they don't need to care about. And another interesting the advantage is the optical switch can also save your capex, in a sense that because they don't deal with packets, you don't need to change an optical switch across the generations of packet switches, like 10G to 40G to 100G and so on. The same optical switch can work. So in a longer run, it can actually amortize the cost, right? Okay, so at least now we have a context setup that the data center is an important context, and an optical like switching can help us. Now, what are the challenges then? So now I will talk about what are the most general existing like the existing paradigms, how people are trying to use these optical switches. So one point to start with, right, that if you think of a data center wide scenario, you have lots and lots of servers. The most ideal thing would be this, because you can change your circuit based on the traffic. If you could monitor the traffic of the whole data center and then tailor-made your circuit, that would be perfect for it. But it's just too slow, right? You need a control plane to compute this. You need to monitor traffic. You have a traffic matrix. You need to optimize certain goals to get something like high throughput or low delay or any such stuff. And then finally, you get some circuit mapping as your output. Now, for a big data center scale, it's really not like scalable. So what they're doing, they are taking an opposite side of solving this problem. Okay, I don't care about the traffic anymore. You give me anything. I want to set up some predefined circuit mapping between the switches with the known properties. And then you do your best to serve your traffic there. Because which is easy, right? Because then you don't have this burden of control plane. So the idea is simple, that you have this OCS here in this green box that will cycle through a predefined set of circuit mapping. What is this kind of simplest form of it is that you just want to give this illusion of any to any connection over the time. You can't give it at every single point of time, but over the time, in average, some Tor pairs have the chance to talk to every other Tor pairs. And it looks like this, that so if I actually split the time horizon into some slots, right? In like T1, you have this connection, A to B, B to C, C to D, D to E, and E to A. Now, at the next slot, you just switch it by one step, like A to C, then A to D, and A to E, right? So basically, you see that that's the thing we need, basically, that at least within this fourth state, every node is at least have some guarantee to connect to every other node, at least once. So basically, the code is going through this perpetual cycles forever with this up and down sequences. So the green means up and red means down. Down means the downtime. So the time scale is quite fast. It's not that slow because now this downtime is 100 nanosecond and the uptime may be like, say, 100 times more. For example, say a few microseconds, for example. So this thing is going very fast through these up and down cycles. This is what we called, very simple, you can guess, it's called a round robin circuit mapping, basically. And the basic advantages that you can do it. It's simple. You don't have any kind of burden of control plane. It's completely like open loop control. There is no feedback going on. And it's agnostic to your like traffic. And it has certain guarantees that it's fair, basically. Every node has a fair chance to talk to every other node, which is the simple starting point to take if you don't know anything about the input. So, okay, this is the setup, and this is basically the table which you are actually implementing here, right? So now my PhD thesis is basically trying to tackle some challenges of this kind of round-robin all-optical course. I will focus on one of these problems now, but let me first summarize. One of the challenges, which is very, very basic with this optical circuit switch hardware, they can only give you point-to-point circuit. They can't give you point to multi-point circuit. That kind of like idea is not there. Packet switch can do that for you. It has IP multicast and all those stuff. So then how to enable multicast? Because what we actually observe that multicast or one-to-many pattern is a very known and ubiquitous pattern in across many kind of applications. In like AI, the most communication patterns are collective. It's not like point to point. What people are doing that to, because they know we can't really support those collective patterns in its original form, they convert it to some simple point-to-point patterns like ring or tree or many other stuff. So that's how they are trying to bypass this problem. But it would be best if you could actually have this real point-to-multi-point pattern directly addressed, right? Because for multicast, you should send the traffic once and everyone should get it, right? And we have the first work of my PhD was basically try to kind of like achieve that. So optical circuits which cannot do it, but optical splitters can do it. So the splitter is basically a kind of a hardware which can split signal from input port to multiple output ports. So it splits the signal power, but the signal is the same. So as long as the power is sufficient for you to like decode the bits, you are good, actually. So I don't go into low level of this work, but that is one part. Like second part was, which is basically our main topic of this talk, which is this, as I showed you, this architecture, this round robin abstraction, what you learned here, right? You can actually guess that it's not the best for diverse traffic scenarios. It has certain properties. If the traffic is matching with those things, it's good. But if not, you can kind of clearly know that you are not at the good state there. So they have lack of like diversity of path, because every node has some chance to talk to each other. You can't talk to everyone all the time. And so, as I said, that this is basically fundamental to the architecture abstraction, right? And we are trying to solve how to compensate for it, because this code is a good thing for you because it is scalable, it's simple. So we don't want to change the core ground up. We want to do something incremental, right? So that it's simple as well as it can compensate for the problems of the core, which we have some works published and some are actually ongoing. So I will mostly focus on this Infocom work now. And finally, there is another problem which you already know, that the optical switches have the downtime. And what we observed is that the downtime, it looks small, but in a very large scale setting, some flows can be absolutely unlucky. That maybe the flow has been launched at a certain time point. It may need to send five packets, but say it sent 4, and at the time of the fifth packet is going out, the downtime comes, because you cannot really kind of like control that. And then from this point of view of small flow, right, you had to go through this fixed price. There might be packet loss, there might be the congestion control happening, which is a bigger, like slower feedback loops and stuff. So that can really impact your tail latency, which is a very, very important problem. So what we actually learned, the average, to improve the average is easy, but to improve the tail is not, and it's very, very subtle. So that is my ongoing work. So overall, right, my PhD work focuses on how to solve these challenges, because if you could solve some part of these challenges, you can make sure this kind of low energy all optical core can be viable in practice, which has good things already we know, right? So now, as I said, I will quickly go through. So the summary of my PhD work is basically adding some components into this holistic space. Earlier, you had server, Tor, and the round-robin core. But in this scenario, right, as I said, for the first part, to solve multicast, we need a separate core using like splitters. So the first work was focusing on that actually. And I will be focusing on this optical edge thing, which is trying to compensate the problem, like this problems of this round robin core using optical edge. So we want to put another layers of optical switch between server and dot. That's why I say it edge, because that part was my edge region, right? And but how to operate those things, it is interesting. I will kind of talk about that more. So there we have some work and we have more to come. Okay, so now let's kind of focus on this optical edge scenario. So as I said, right, the kind of the problem of this optical edge was connected with this round robin scenario, absolutely like this abstraction. What was the problem? So let's try to have this anatomy of this round robin architecture. So again, this like thing from there, you can see this is completely the bandwidth spreading is uniform across the TOR, which is good if you don't know anything. But the data center traffics are not completely unknown, also not completely known. You know something, you don't know something. So obviously you can exploit those information to support this traffic better. So if your traffic would be uniform, you would have fair utilization of this kind of like the circuits. That's great. That's a match. But in practice, the realistic data center like workloads, they are not uniform. They are highly skewed and they are heavily inter-rack. So skewed means not every TOR pair are exchanging the same amount of like data all the time. Very few rack pairs are talking a lot. Most of the rack pairs are silent. And you can actually see some like evidence from some practical traces. Like 80% of the traffic is between less than 0.4% of the rack pairs, right? And many more. And similarly, the traffic is not very, very local. So generally, the servers who are actually far apart, so they are not under the same switch, they actually communicate a lot. It has many, many causes. One of the simple causes like fragmentation. For example, you don't have the luxury to place it very well all the time. If you could place the job properly, you would try to do it as local as you could. That say you need 10 servers, you try to have 8 from the same door and maybe 2 from the next door. That's one of the best thing you could do. But if you don't, generally because of these dynamic patterns of applications coming and going, you have some fragments left here and there. So you need to place it anyway, right? And that creates this inter-rack traffic. So more than 95% traffic can be inter-rack. So you see that lot of traffic is using the core, and the code is a mismatched core with the traffic which you are trying to handle. So that's what we are trying to solve here. And the thing that we are showing that you see like how bad this performance can be under this like practical traffic scenarios. So for that, we have a packet level simulation with some practical cache traces. What we do here, our baseline is a round robin all-optical core like Sirius, which is one of Microsoft's work. And we actually compare it with an ideal non-blocking packet switched core, which would be the ideal for us, right? And here is what we are plotting. We are tuning the skewness with this 2 parameter x and y, which means x fraction of the rack pair are sending y fraction of the traffic. If you make y higher, it means the skewness is higher, right? And you see, we are plotting the average flow completion time in microsecond for each of these 2 architectures, right? And you see this blue bar is growing up quite fast, right? And this is what the summary is. Because of this impact of skewness and high inter-rack volume, the average slowdown can be around like 7 times or more. And obviously you understand why, because some hot rack pairs are heavily utilized and kind of like congested. But there are many other rack pairs which are not used, right? Because they don't have anything to send. And because of this round robin abstraction, it actually forces you to use only those hot rack pairs, right? So you have bandwidth there. So the problem is not about the bandwidth, but you cannot use the bandwidth in a kind of a granular manner. So that's the problem. Okay, so let's see what to do. Like there is one state-of-the-art way to improve it a bit, which is basically try to use some indirect hops. Because you see that it's fine. I need to send something to you right now, but I don't have a direct circuit with you now, but I have circuit with someone. And that someone can have a circuit with you very soon, like earlier than you and I have a circuit. So that is one of the simplest way to handle it, which we basically called variant load balancing. I will show you. So the basic case, right? This is my table. This is my round robin pattern. A needs to send this packets to B. The simplest thing will be you should use like time slot 3 because that's the first time A connects to D. So basically, even with this toy example, the first packet needs 3 slots to reach, 2 slots to wait, and 1 slot of actual sending the data. But instead, what you could do this. You could send it through an intermediate TOR. For example, you can send it to B at time slot 1, fine, and then B can send it to D at time slot 2. So B is connected to D earlier than A. So even with this simple case, you see that you can save 33% of the delay, right? So in a kind of a longer case, you can actually think of this as a pipeline. So some node AX needs to send something to Y, and it can actually send through each of the other nodes in the network. So it can use the network as its queue, basically. So all nodes can buffer for some slots and then kind of like forward. So there is a diverging state and there is a converging state, which is much faster than sending only at the direct hop and to wait a lot, right? Yes. So basically, it's still like one packet, right? So basically, it's not the copy of the same thing. Say one node needs to send 5 packets, right? So for the first packet, you send it to B. Second packet, you send it to C. Third packet, you send it to D. And parallelly, B is connected to D now. In the next slot, C connected to D now. E connected to D now. So you are actually spraying the packets across multiple nodes. And they can buffer, obviously, because these are your TOR switch. These are still your packet switch. They can queue your packet, but they will forward it at the respective slot when they will get connected to the proper node. So it's not the copying; it's just the same packet, but you need to buffer it. That's true, right? So in the first case, you had to buffer it at the source because you have small chance to connect. Uh-huh.
That's what you need to be able to get it directly. Versus K other nodes to which you split your packets, then being connected. The limitation seems to be that the destination should be connected. I'm curious to understand how you get a gain. Where is the gain?
Okay, so basically, okay, you see, like the gain is from here. So this pattern, this circuit pattern here, right, which is basically a pre-known pattern. By that, you are actually operating this. So these patterns are not random. So this is basically what we call round robin pattern, which is this state-of-the-art scenario. So the goal is, because you cannot have everyone to connect it to everyone using circuit, so let's connect one by one over the time. So in this 4 time slots, A connect to B, C, D, and E, right? But this cycle will come back again and again and again. So now you think A needs to send something to B or D, say here. So if you want to send it directly, like always, in the first cycle, use the time slot 3, send a few packets. In the next cycle, use the time slot 3 again, send some more packets. So you see, between this T3, 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 you have some waiting slots. You just cannot send anything because your routing algorithm says you have to use direct hop. But the idea is, probably you could use some intermediate node who connects with the earlier than you. For example, here, right, that B connects to the earlier than A. So that way you can save the latency. Obviously, it's not the best for the throughput because there is a game here being kind of like going on. So in a very, very general sense, for a bigger flow, right, on average, they are taking two hops. So your throughput is half, roughly. Your worst case, like throughput can be half. But here we are more kind of interested about the delay because that is one of the important metric for many data center jobs, like the applications. So there, from the point of view of the latency, you can save time slots, right? Is this fine? Thank you. Okay. Sorry. I think the Valiant is the name. Okay, so I have actually checked it, but I guess some person called like Valiant probably made this. So the Valiant load balancing, this idea is not attached with this. This is a very general idea. The paper was from 80s, I guess. So this idea is you are just using some intermediate nodes for any purpose. And people have used it here. So they just borrow the name actually. Okay, so yeah, so you see the path is now longer, right? But you are taking the advantage of intermediate hop to save the delay. Okay, so let's see how VLB can help, because earlier we saw that the slowdown was too much, right? Without doing the VLB. So now again, what we did, we added the VLB on top of this round robin core, right? And here is what we see. Now, for the one-to-one scenario where the core has the same bandwidth at the edge, VLB can really help, right? Because you see that it is really close. So we are plotting the slowdown compared to packet switch case. The slowdown is very less. It's 33% average or 74% for the tail. But the problem comes when you have higher and higher of this, like the oversubscription at the core, because this technique is a common technique the operators use to save cost. You just don't need that much of bandwidth at the core because not every traffic is going up always. So under this oversubscribed case, because you are taking intermediate hops, you are most likely to go through congestion actually. And that leads to this fact that, for example, for this 8-to-1 scenario, the slowdown can be more than 10 times, right? So as I said, the root cause is coming from two aspects. The intermediate node is congested, and it cannot reduce the inter-rack traffic, because whatever traffic was inter-rack, it's still inter-rack, right? Because you don't change the location of the servers anymore. So now this question is how to efficiently support. So VLB can help you, but not much. You need to do more to actually make the gap lower compared to the ideal. So here comes our idea, which is intelligent traffic regrouping at the edge. So let's try to take early action, because you know what your code is best for. So let's reshape the traffic from the edge already, so that when it reaches at the core, it is already a good match with what kind of traffic the core can handle well. So the idea is this, that we are putting some optical switch between the server and TOR. It is not a traffic agnostic plane. It is adaptive to the traffic, but in small scale, because it's not an overall data center scale. It's for some set of servers only. So what it actually enables you now, you can regroup the server under some TORs. So it means the servers are not perpetually connected to one TOR for its lifetime. You can change it actually. And you see that if you regroup the server, you have two things to play with. One is you can make inter-rack traffic volume much lower. You can localize traffic. You can localize servers under the same TOR who are talking a lot. So that already makes the burden from the core much lower. And the second thing is you could rearrange the servers in a way that the inter-rack traffic becomes much more close to uniform, because you know that this code is great for supporting uniform traffic scenario. So these are the two games to play here. Like, can we come up with an algorithm here, which basically our ASV minimization algorithm does, which we call skewness and volume minimization, is that we want to minimize both of this at the same time with a proper balance. We can localize most of the traffic under the rack, so then the volume of traffic is lower there, and whatever traffic is going, because we cannot localize everything, some will go up. So can you rearrange those traffic, inter-rack traffic, to make it more uniform than skewed actually? So this is basically a traffic shaper you can actually think of, right, by changing some optical circuits between the server and TORs, so that you can compensate for the problem of the core actually. So that's the goal. That's the very, very high level paradigm wise goal. So, oh my God, so I think some of the slide got a bit messed up while transferring, sorry. But okay, so the idea is, so the kind of intuition is simple. The skewness, minimizing the skewness and maximizing the locality, they are not really independent parameter, which I will show you here. So which makes this problem tricky. And if you always greedily go to localize the traffic all the time, you can do more harm than good at the end. So let's see how that thing is basically we can prove. So for example, say you have a small example with 3 TORs and 2 servers under each. So total 6 servers. And these are your flows from server X to server Y, and that's the flow size. There are some big flows, some small flows and all. So now initially, you don't, so that's your kind of like your initial state. Initial state is your config A, which was something like this. And that is a very bad state because you see most of the traffics are indirect, right? And they are not really arranged properly. So you can see this, how we measured this. This localized traffic is like 0. There is no self loop. And second is, we use James fairness index of the indirect traffic values to measure the variance of it, basically, right? The higher the variance, the higher the skewness, the lower the JFI metric. So you see the JFI is very small. The highest can be 1, right? So the traffic is skewed and like indirect. Now, if you would actually, why it's not moving? Maybe I can use this. So now, if you actually go for naively localizing it all the time, you would come up with some configuration like this. You see, most of the flows are self loop now. That's great, right? The locality is very high. But some flows which you could not localize, they are centered on some links, which is the same problem of skewness again. So you could not improve skewness. Your JFI is almost same or worse, actually. So instead, what you really want to come up with some kind of symmetric configuration like this, where you opportunistically localize flows, which will help you more. For example, here F1 is a very weak flow. If you localize it, it reduces the burden from the code a lot. So localizing that is really good for you. But you don't need to localize everything, right? You can balance the indirect traffic in a more careful way. You see, I don't localize everything here, but they are arranged in a very, very symmetric manner so that the JFI has improved more than 3 times already. So it's, you reduce some traffic from the core, and at the same time, the traffic which is going out, you are making them as uniform as you can. It's not perfectly uniform, but it's still close. So that's the trick of this ASV minimization paradigm. That's right, yes. So here, basically, for all these indirect traffic values, right, we are just using them as X, and basically we take the average square by the variance. So that's my JFI. So it's just the JFI of indirect traffic, right? So it doesn't have any unit at the end then, right? So we want to make it as close to 1, actually. So what we really need here is that we want to solve this problem by making a right balance between these 2 sides. We can't. I'm sorry, which one? Right. Yeah. So here, for this case, we don't have the time-based analysis here, but for the actual like the experiment we did, there we could see. But if you want to like model it, it's more like earlier, right? If you can think of this all-optical core again with some time slots. So now, for example, if you need to send this big flow through that core, you can have this wait slot and actual slot, and you can add those. So that will be the delay model for it. Versus if you directly connect it under the TOR, all the wait slots are gone. So that's how you can actually have 1-to-1 delay for every flow, and you can plot the average, tail, whatever, right? But thank you for asking this question. Right. So now with this, the question is how to make the cost function then, which can actually capture these 2 essence. By English, we actually understand this, but by math, we need to kind of like formulate it. So again, if we kind of like focus on these 2 setup, like config B and config C, from the point of view of F2 and F3, right? You see, for config B, it was bad because F2 and F3 was centered on the same link. But for config 3, see, magically, F2 and F3 are separated. And that's what we want at the end. Now, how to do it? So a linear function cannot do it for you, because if you just see from the linear cost point of view, that is just simply the indirect traffic, the sum of it, right? If you just take the sum, in both cases the sum is the same actually. So it's 1000 plus 1000 anyway, right? So it only penalizes the overall volume, but not the variance of indirect traffic. So what you actually need, oh my God, the slides got really messed up. We need we need some cost function that will penalize the first one and helps the second one. So phi of 1000 plus phi of 1000 should be strictly less than phi of 2000, which is centered actually. So that's some kind of cost function we need. So overall, we need a superlinear cost and strictly increasing function that can probably penalize this first thing and converge your solution towards this side. And that's what we did. We actually have an exponential cost function of indirect traffic mx. Okay, so the x is your indirect traffic load actually. So the high level idea is, at one hand, exponential function can give you higher cost if the indirect traffic volume is higher, and at the second time, it also penalizes you if the indirect traffic variance is higher because of this superlinear and the properties of this exponential function. So the goal is to find this optimal server-to-tower mapping, which will minimize this cost. And what we really observed that this worked very well. So I will take maybe 10 more like minutes quickly. So I will go through quickly about this part. So this is basically now the formulation. You have the crux now. So this is my phi actually. That's my cost. And this overall cost is the indirect traffic multiplied by this cost for unit indirect traffic value, right? So if you objectively minimize this cost, it will give you the right balance to optimize your skewness and the locality of the traffic. And based on which server are connected to which TOR, you can always find out the indirect traffic between TOR I and TOR J, right? So what we do that here, basically, we just came up with a hill climbing based randomized heuristic, which is quite fast and actually converging pretty well what you actually observe. So the idea is simple, is that what you need to do, you need to rearrange servers, right? So the basic step is you swap two servers. You take two servers from tutor and you like swap it. That's the smallest step you can take. And if that change is making your cost lower, you actually accept it. If not, you don't accept it. And you kind of go through it, right? And what we actually observe that it kind of converges very well because of this property of the cost function itself, right? And on top of that, we have kind of optimized a lot to make it faster, because one of the things is whenever you make a swap, you actually want to compute the delta of cost, and you don't need to compute every time from scratch, which takes like square of the matrix size. But you just need to compute the proper entries of the matrix, not all the entries, because you're just changing two server from two TORs. Not all the TORs are touched. That makes one order of magnitude faster for us. And also on top, we worked a lot from the to kind of implement the code, implement the cost function. We actually implemented in like C++, and that takes us like microsecond scale even on a single core like CPU. So you can put it on hardware, it can be extremely fast. So that's the idea. Now I will quickly go through the results. So we have evaluated many things. We have like the simulation, we have power and cost modeling, we have real test bed implemented. And these are some kind of like parameters. So the scale is 32 server per TOR. We have like 16 TORs and more than 500 servers. So that's the scale. And here is what we see. The first thing is the performance itself, the delay, basically. So you see that across the oversubscription scenario, if you focus on the green bar, which is ours, and here the violet bar for 1-to-1 is basically the best performance you could achieve by a non-blocking packet switch core. And you see we are actually very close. So the average is within 6.4% of the ideal. And even at 8-to-1, we are only 47% worse than the non-blocking core. So it's 8 times lesser bandwidth, but still we are maintaining performance very close. And at the same time, obviously, this is a kind of idealistic scenario where we consider one big optical switch at the edge to see the upper bound performance. If we split it into small case, then you have lesser flexibility, because now each server can move to a certain torus, not all the torus. And there also we observe, if you focus on the green bar, the performance is almost like similar because of the cost properties and stuff. So it degrades by less than like 2%. Although if you could go for localizing stuff, you see that you would actually suffer. The red bar like goes up. And finally, it doesn't need to add lot of energy and cost. Surely it needs to add something, because we are adding some optical switches at the edge. But optical switch power is much lower than packet switch power, right? So that gives you this green bar, which is the excess percentage of power you need, compared to not adding anything, right? Which is much lower than over provisioning the core, because that would be one of the simplest solutions. Just throw money at it, give more and more bandwidth at the core. But that would have much more energy, much more like the energy and cost, both. So we are always less than 50% of extra power. As well as for the cost, this orange bar, for more of this like the realistic kind of the setting where the optical switch price is a certain fraction of packet switch price, because the problem here is this: packet switch is commercialized, but optical switch is not fully. So you can't really get the real cost of it for the mass scale scenario. But whatever data we get from there, we actually vary this cost as a range, as a function of packet switch cost. And even if the optical switch cost is more than 60% of the packet switch cost, the red bar is the lowest, actually. So for a realistic setting, right, the over provisioned optical core will have much kind of costlier compared to the edge, right? And as I said, that across the over the time, it can save you even more, because you don't need to change the optical switch. So that's the summary, right? Overall, that optical circuit switch can go a long way, and OSAP, this optical edge, can actually compensate for the problem of this all-optical core. And it can save your power, it can give you high performance. So with that, I would stop, and thank you so much for attending.
Thank you, Dr. Das, for delivering this interesting talk. Are there more questions from the audience?
Yes. So the data that I showed you here is from the packet switch, like emulation there, where we really like simulate packets. We have implemented the architecture, the VLB routing, and all this up and down stuff, right? And we send packets. Also, I have implemented in our test bed. So we're at RISE. We had a real data center with some servers and packet switch and a MEMS switch, actually, and MEMS-based optical switch. So we have actually run a matrix multiply application there, which is where you know the patterns, and based on that, you can actually configure the edge. So we actually did that, yeah. And that also shows similar stuff for us. Thank you.
How would it look like? Where would this edge live?
So physically, right? So physically, the edge would look like, so I mean, if you see my first slide, right, the servers are in the rack, right? And then so for now, you just have a top of rack switch there. But so now, instead of directly going there, you can have an optical switch for certain racks, which you can call an optical rack, maybe. And then all the servers of that zone will get connected to the optical switch, and then optical switch will connect it for the rack. So then basically what it gives you something like this, right? That you can still emulate your generic connection that you have already, right? If you don't change the circuit, that's fine. But now you can actually change the circuit here, and that will change the actual mapping. So the server location, the power and everything are coming from the rack, but it's just the connection, the network connection, the fiber that is going through this optical switch box instead of directly going at the TOR. I don't think so, because I mean the point is the size of the rack actually, and the length of the fiber there is a few meters basically. So that's the scale of the racks we are kind of like talking about. I mean so that is already there actually. So I mean these days, because we are actually operating at like 100 gigs or 400 gigs, the copper wire cannot work anyway. So you have like transceivers and fibers attached already. So it's just the optical switch you are actually adding. Yeah. Surely for 10 gigs and stuff, you could use those copper wire, but at this scale right now, fibers are everywhere inside the cluster.
Any more questions? Thank you everyone for attending. Have a great evening. We have arranged refreshments in the coffee here. Please continue your conversation there. Thank you.
Thank you so much.